Well, thank you everybody for coming on to the webinar. I'm Cameron Croft, and today we're going to be going over cooling for natural gas processing, the webinar. To stay in the know, so if something happens, you couldn't make it today, we will be throwing this on our YouTube channel. We're shipping out links onto future newsletters. So if something happens, kids walk in, if you're working remotely, power shuts down, we will still have this information. And then if you want to follow up at the end for specific questions that you have on a well site or something that you have going on, please feel free to reach out and ship that to us so we can get those things answered. We do have a blog that allows the video to be in transcript form if you don't want to watch the whole video, and you can do a control search find and just find exactly what you're looking for and move on. That's going to be in the blog, so you'll see the video and the transcript below. Now, I'm going to be joined today by our brilliant speakers, Charlize Sparks and Chris Smithson. Charlize Sparks is our research and development engineer. She handles all of our proposals that come in, the back and forth with our sales team to make sure that the clients are getting exactly what they need. And we have our chief technology officer, Chris Smithson, who recently got promoted to that position. So now he gets all the blame if there's any failures in our company on the technology side. So now for the webinar structure. In this case, we do have the question and answer. If you're new to Zoom, there's a question and answer box and there's a chat function. So while they're going through the content, if you have a specific question or if you want them to elaborate or follow up on that, you can please put it in the question box or put it in the chat function. And then that way we'll make sure when they're having a natural lull that I'll be asking those questions for them. Today's topics, we have cooling for efficiency and profitability. We have natural gas coolers and utilization and design requirements, common issues, and troubleshooting. Now we are going over that content, but I do have a side quest. So I put up a series of dad jokes to kind of shake things up a little bit. And I really want to hear Charlize because she has a great dismissive scoff when she doesn't approve of something. So I'm going to try to figure out on the scoff level which joke that she finds more dismissive than the other ones. So you ready, Charlize, for that?
Yes, absolutely.
I know you are. All right, so Charlize, how about you kick us off of our first topic is cooling for efficiency and profitability.
Okay, so we're getting started with cooling for efficiency and profitability, mainly because, these things are going to go hand in hand, efficiency and profitability. If you have a system that's, really efficient and it's doing what it really needs to be doing, then you're going to have things like your, the cost of your system or whatever goes into your system, you will have less costs going into that, or let's say less cost for repairs. So that's going to be saving you money when your system is working the best that it possibly can. So three things here. We're going to look at gas temperature initially, just sort of an introduction on that part, and then we'll go into what contributes to our efficiency and our profitability in that.
I did practice on my son last night, and then I was explaining this to him. He's 11. So his first dad joke that he came up with is, so you're teaching people on how to learn to chill. So on a scale of 1 to 5, how bad was that? One
not
being
bad at all.
Oh, you're just saying that because he's 11.
It's wonderful to be able to know how to chill.
Yeah, learn to chill. Okay. I'm going to keep that one though. Now, gas temperature. Let's dive into that. So yeah, Charlize, take the lead on this one.
Okay. So for hotter gas, just in general, it's going to hold on to water vapor. And so if that happens, that's usually going to be a problem downstream. So in your processes and what your systems can handle. Looking at the water vapor content chart here on the left-hand side, you'll see that just really at any pressure, if your temperature is up higher, you are going to have water vapor content higher. And so what we are trying to achieve with this is just explaining that, if you have your ideal gas temperatures going into your systems that are lower, you're going to already be starting with a lower water vapor content there. you'll see in gas production coming off the wellheads, you're going to see in excess of 130 degrees Fahrenheit in a lot of cases. And then, more especially in the summer times when, especially here in South Texas, Louisiana, we can have summers seeing up, way above 100 degrees and 100% humidity. So you're going to want to make sure that you have your coolers on hand so that you can have your gas temp going into your systems at an ideal temperatures. So right here we have ideal temperatures of about 80 to 100 degrees for your most efficient processing.
Is there anything you want to add on to that, Chris, on these charts?
It's good. I mean, water saturation, the hotter it is, the more water it holds, which is definitely going to drive things like dehydration. But, from hydrocarbon dew point sense too, I mean, the hotter it is, the more hydrocarbons it can hold too, which when you're doing rich gas can make a really big difference in trying to separate and process and keep equipment running.
I know, so gas temperature, it seems like that, I mean, that's one of the biggest swings. I guess when you're doing a proposal, do you see the gas temperatures, is it the easiest thing to manipulate? Pressure seems to be, like, I know you got choke valves and back pressure valves and stuff like that, but what do y'all feel on that? Is temperature the easiest thing that operators could manipulate to help out processing?
Yeah,
it depends
definitely.
on their operations.
Yeah.
Yeah, I mean, it's how's it set up? What's causing the heat? Where can equipment be placed? Maybe mitigated ambiently versus pressure. Maybe a choke. Just adding a back pressure valve can be cheaper than adding a cooler. So it definitely varies from site to site. What's causing that temperature increase and what other parameters maybe you can tweak to really knock it down.
What were you going to say, Charlize?
Oh, no, I was just going to say that, similar to what Chris was saying, it's obviously going to be where your gas is coming in, your placement of your cooler, and also just how hot are you, where we've seen, kind of, if they're coming in at 80, okay, then that's pretty ideal, but we've seen 130, 140, 150, and even in some, small cases where they've been 200 or more, so. It's just going to depend.
I know this is water content. So the temperature does affect water content, affects the saturation. And the next one is hydrocarbon dew point. So temperature affecting that. So Chris, do you mind taking a lead on this one and telling us a little bit about this?
Yeah, so the hydrocarbon dew point really comes into effect when you have richer gas. And that's pretty much the temperature that you're going to make hydrocarbon liquids as opposed to water liquids with saturation levels. And this can be depending on what your temperature change is, it can mean a lot of liquid falling out in the wrong spots. And so, initially cooling it down and then separating properly afterward can keep a lot of that hydrocarbon out of your systems down the line. So, hydrocarbon dew point is a good thing to look at if it's on an analysis that you can read or run it through a simulator just to see what that is, just to see where and if you're going to have liquid fall out and what the concern might be there.
So I don't know how to say that word. Is it cricondotherm?
Cryocondotherm?
Cryocondotherm.
Yeah, it's pretty much the sweet spot pressure for the highest temperature you can get and not make liquid. So it's the, if you're anywhere within that bubble, then you're going to make liquid. So if your target, and basically when you get cold, that whole bubble shifts based on whatever temperature you got to. But that's kind of when you're going to make liquid if you're anywhere within that. Which if your gas's methane content is in the 70%, then that's something you're probably going to want to look at. If you're in the 80s, then it's a little more dependent on how cold you're actually going to get. If you're in the 90% methane range, then your gas is probably lean enough. It's not really a concern. But yeah, down Eagle Ford, Permian, the richer parts of Oklahoma, those areas can really, hydrocarbon dew point can really make some problems for you.
Right, and I guess what was the apex, that top one, Krakendabar?
That's that one doesn't really affect much. Usually it's pushed into a pressure range you're never going to see.
Oh, how do you say that?
Krakendabar.
Now, so you could be making that up, and I'm probably not going to know. You could be BSing me right now.
It's out of a very expensive simulator program, so. Someone's
No.
tricking me and taking my money if that's a made-up word.
All right, so the hydrocarbon dew point. So temperatures affect water content, water saturation, and then you're talking about the hydrocarbon dew point. So that's the heavies, right? The liquids that could fall out in liquid form.
Yeah.
Okay. All right, so in efficiency and profitability, you broke it up into 4 key areas. Charlize, can you explain a little bit about this, and we'll jump into the next section?
Okay, so for each of the systems that we're going to sort of be talking about are these 4 things are factors where you're going to see the where you need the most efficiency in order to get that profitability. And so one of them would be the unit itself, whether that's sizing or just the arrangement. And then the second one would be consumables, if that's, part of your system, whether you're going to be using more or using less, or you're going to have to use a different chemical that's more expensive. For 3, wear and tear, it would just be, obviously hotter temps are going to do a little something to your instrumentation, or they're going to make things overwork. So there's be a wear and tear on the system.
Mm-hmm.
And then number 4 for your regular maintenance would be just if you're more efficient, then it's going to contribute to hopefully less maintenance. You're not going to have your guys in there that are having to swap out anything or, refilling your system more often. All those things contribute to added costs.
So in those 4 break things, we got separation right now. Who wants to kind of take the lead on that? So we're going to be talking about separators or bulk separation.
Yes, I'll go through on this one.
Okay.
So for separation, I mean, if you're looking at the worst case liquid load capacity and you're expecting your temperature to be 120 degrees or 135 for this example, and then that temperature cools through there and it's actually coming out at 100 degrees, you're gonna have a lot more liquid. On a rich gas analysis, like this is a very rich gas analysis, it's 62% methane content, real high percentages of the other heavies in that gas stream. So when this gas cools, I mean, it makes liquid at any amount of cooling. It's the hydrocarbon dew point's 140 degrees in this example. So any % drop in temperature is going to mean liquid falling out. And separation, just adding separation isn't going to help anything with hydrocarbon dew point or water saturation. Water is a lot less than hydrocarbons for what you can squeeze out of the gas if you cool it. But it doesn't matter how many separators you've put in there. In this example, we have a simulation run where we put 4 separators in a row, and they have not even 2 degrees of cooling between each separator. We basically drop about 5 degrees to this whole line, or 4 degrees to this all 4 of them. And even that, the last one's still making over 600 gallons a day of liquid. So separation isn't going to solve your liquid removal problem if you still have any sort of ambient cooling happening, which means you need more separation, which means you may need scrubbers added ahead of other units to protect from them. They may need to be a certain size that you didn't plan for when you're putting them out there to protect those units. So really understanding, or if you can pre-cool down and separate and then go into that equipment, then it makes this downstream equipment a lot smaller because there's a lot less potential liquid to fall out. But if you're waiting for it to kind of fall out on its own, then you never really know where it's going to end up if you're if it's just ambient conditions that are driving that. So separation can be really important to remove all this stuff, but knowing the best place to put it and how to optimize for that's really important.
I know you got the bulk separation usually in the beginning, like the big slug catchers and stuff like that. I mean, do you recommend putting some type of cooler beforehand? I mean, some people don't want to cool it off just because the hydrocarbon dew point, they want to try to collect it and go into some type of storage tank and sell it later on. What are your recommendations on that for separation then?
Yeah, I mean, there could be requirements to where you're not really allowed to cool it or actively remove the hydrocarbons that are in the gas. I mean, you kind of have to balance that against, what your operational conditions are. I mean, pipelines also have hydrocarbon or temperature spec. So, you need to stay within that. But if you can separate it and sell it as oil yourself, then you're usually going to make more than sending it down the pipeline and letting them pay you for it. But as far as cooling, you usually want the bulk separation to happen before the cooler. That way you get rid of all that liquid. The liquids should take a lot of heat. Usually the hotter wells are going to have the most liquids. because it's a liquid that's bringing up the heat with it from underground. So getting the bulk liquid out and separating that away, then having your cooler and then another separator to separate what you condense is usually the best way. It's also the easiest on the cooler too, because a bunch of liquid going through the cooler may cause some operational issues or damage to the thin tubes.
All right, so I know separation was the first line. Let's talk about, Shirley, you want to take the lead on dehydration and breaking it down to those 4 key areas that you were talking about earlier.
Okay. So for dehydration units, and Chris sort of mentioned, he touched on this a little bit. When it comes to your unit, your higher temperatures, they may require you to have larger vessels, a taller vessel, and a taller vessel will need, or a taller tower is going to need more packing in it. And that's going to be what creates your efficiency so that you get good desiccant contact. And that, that's going to mean bigger diameter, taller towers, more packing is going to mean more costs in that specific area. So then when we want to talk about consumables, your lower temperatures will allow for your best utilization for your consumable desiccant. So we have an example here. Our Croft system, our passive dehydration system, will require filling in higher temperatures. You might see filling every 2 to 3 weeks versus if you have a cooler and you have those lower temperatures going into your system, you can see more efficient out a month or 45 days before you need to fill again. And then also with consumables, your higher glycol losses here, because your triethylene glycol is going to stay entrained in your stream, and then you won't have that proper separation in your tower and back to regeneration. Or in some cases you might have to go tetraethylene glycol, which is more expensive for the drying that you're going to be looking for. And so then, when we're talking wear and tear, when we're going to be, you might be overworking your pumps with that higher temperature. It's going to change, viscosities that require, more work on your pumps. And then you'll need to be changing out your filters more often, just because those higher temperatures aren't going to work well on your filters. And then same thing where your instrumentation is gonna, for example, you might have to swap out your level indicators or just something, that you're not going to be able to, with that temperature, it's just the function of it isn't going to work properly because it's not all of your things following in your system and going downstream. They're just going to not indicate what they're supposed to be doing. And again, so regular maintenance, same thing. So if you have all your consumables, your wear and tear, your service guys are going to be out there more often, which is probably good for them, but then it's not good for your own profitability, right? Profitability. They're just going to be out there more. They're going to be having to swap more things out. You're going to have to be purchasing more things that go into your system. So.
Well, I was always told like a good rule of thumb in the field is for every 20-degree increase is doubling the amount of water that's in it. Is that accurate?
It's accurate on, yeah, it depends on the actual temperature drop. Like 80 to 100 degrees is a different amount than 100 to 120. So it's a little bit of a curve, but yeah, for the most part, that is accurate. But basically, yeah, you're doubling the water content when you go up 20 degrees. So 100 degrees versus 120, a unit to do 120 degrees is going to be twice the size of a unit that will do 100 degrees max. So that means, the tower doesn't necessarily change in diameter, but you may have to add, instead of an 8-tray tower, you may need a 10-tray tower. If you have really excessively high temperatures, if you like 125 on your inlet gas, then your standard 8-tray tower may not be big enough. If you're oversized, maybe it is. But yeah, you may need to go up to a 10-tray. And on the regen, I mean, you're doubling the size of the regen because you need to double your circulation rate if your regen's at max. So then that can be the regen's a big cost there. So that can be doubling that. And then it doubles your emissions, doubles your pump size, which is probably going to double your cost on pump rebuilds. Not to mention the higher temperatures, just hotter glycol going back to the pumps means it's going to wear the pumps out faster too. And then you're going to be swapping your pumps more often. So
It'd be important just, I know the whole purpose of a dehydration unit is to move as much water content from the gas as possible, getting in pipeline spec. So if you're going to do that, just to kind of cut the effort in half of your dehy, you would like to get an ambient cooler, powered, non-powered, anything above or upstream of the dehy. Is that what you recommend?
yeah. And even on like, I don't know if it's this exact site where this picture of this TG is, but when they turn their cooler off at night because they didn't want to put a bypass on it. And so during the daytime when that cooler's on, we're at 2-pound outlet on that dehy. And then when they turn the cooler off, the temperature jumps up 15 degrees and we're at like a 6-pound outlet on the meter. So, and we don't change the circulation rate to make up for that or anything. And, maybe if we did, we could squeeze it back down a little bit, but then that means someone has to, mess with the unit every day. But just that, we went from completely in spec to barely in spec, just with that temperature change.
Well, most of the pads, Shirley, so most of the pads are square, right? So that's why I tell my clients that as long as they put their dehy in the corner of the pad, it's always going to be 90 degrees. How bad was that one? 1 to 5.
I'll give that one a 3.
All right.
I give it a 4 because that's just incorrect information. we're gonna quote them the wrong thing.
I know. It's 90 degrees. If I have to explain that, it's not that funny anymore. All right. So JT plants, let's click onto that one. All right, JT plants, temperature effect. Shirley, do you want to take the lead on this one?
Okay. So again, when we go to just our unit in general, our higher temperature inlets are going to make it harder for your JT to get that cold separation that you're looking for. It's going to require a greater pressure drop across your system. And so in this case, if you don't get that cold separation that you're looking for, that's going to decrease in your liquid recovery. It'll require more methanol injection. And then you'll get that less desirable BTU reduction that one of the purposes of your JT plant. And, again, here with your wear and tear, it's really kind of the same things along the lines of your dehydration system. You're gonna, you want all of your instrumentation to be properly functioning. And when you're not getting those ideal temperatures for your instrumentation, they're going to not do what they need to do, or they're going to, wear down, break, and they're going to need more replacing more often. So again, with the regular maintenance on your JT systems, if you aren't coming in the way that your system is working its most efficient, then you're going to need that more regular maintenance.
So when you're getting a quote coming in, JT is manipulating pressure to try to get the desired output temperature that you need to for the liquid fallout and whatever you're trying to do, recover, BTU reduction or recovery. I guess, what do you say if it's coming in at 120, 130 degree gas? There's only so much you can do on the heat exchanger efficiency and the amount of pressure drop. So I guess, Chris, what would you suggest on that?
I mean, it depends on what you're trying to achieve. I mean, if your BTU requirement isn't that low and you're just trying to, clean it up for, a little bit for an engine that doesn't have that much problem with that for fuel gas, and you just kind of want to kind of spread that hydrocarbon dew point out a little bit so that you're not that close to where you potentially make liquids, then you'll probably be okay. But if your whole goal is liquid recovery and you want to make as much as you can, then cooling it down is going to make you a lot more money. What we've seen in the JT simulations, when you get below -20 or when you get below 20 degrees, you actually see an increase in recovery because you start to pull out more propane then. And so there's a difference percent wise. If you're like 25, 22 versus like 18 or 15 degrees, you're going to be making noticeably more liquid once you get below that 20 degree point. And so like if you can add a cooler and it's a difference between 25 degree operating temperature on the JT versus a 5 degree, then you're going to see a noticeable decrease in your BTU and a big increase in your liquid recovery. So if your whole goal is to make more money, then you need to get colder with it. The unit's only rated at -20, so you don't want to go below that unless you have to build a custom unit. But you can recover that cost pretty quick if you're if the whole thing is making money by adding a cooler, especially on the smaller units, if it's an ambient cooler, then that's a pretty quick payback on that.
Well, the JT talking about that, but the chemical injection's a little hard to figure out what temperature doesn't affect the actual chemical, right? Well, I'm jumping into it. I'm gonna let y'all get into it. Charlize, you want to kick this off?
Okay. So for chemical injection, and when you're talking about your unit, just kind of what we were talking about in separation, you're going to want to cool first and just do that initial separation for your condensate removal. But when we're talking about how, Cameron, you just asked if it's going to affect your chemical injection, you do still have sort of ideal temperatures that you want your chemical itself and your gas to be, so that they can have proper coverage when it's spraying chemical and better contact. So still here, you're going to still want, these ideal temperatures between, 80 and 100, where it's going to be able to do its job. Temperature always directly affects viscosity for a lot of different, liquids. And so you're going to want to get that just right so that allowing it to do its best job.
Now,
and then
go ahead, Charlize.
Oh no, I was just, to touch base again on wear and tear. It's the same thing, as our systems above, just to make sure they're properly functioning, and because your temperature is going to affect some of the way that these things work at times. So again, you're just that contributing to your cost factor. You still want to maintain, or be able to get the best out of them, and then maintain them properly.
Yeah, I know you, so we kind of built our chemical injection systems based on, we talked to several chemical companies and trying to figure out, I guess, their lessons learned of what affects most. And they were saying like displacement from actual liquid fallout makes it where their chemical is not making contact with whatever they're treating for. But Chris, can you talk a little bit about that? I know we got a picture here, but can you talk a little bit about that, of what that led into our design and why we thought that was true?
Yeah, so in the picture here, we have our chemical injection system, which injects a liquid scavenger for H2S removal into the gas stream. And we have an ambient cooler attached to it as well. This was very rich gas in the Eagle Ford where we had these units, and the condensate in the system was falling out everywhere. I mean, it was, I think this was in winter time when we were out there on the startup for the site. But on the initial site that we trialed, we would see liquid caught in all the scrubbers, in between different equipment. We had a dehydrator on the site as well as a fuel gas skid. And there was, just because the gas was so rich, any amount of ambient cooling was causing liquid fallout. And when you have that liquid fallout in the system, you have liquid either flowing annularly through the pipe, where if your velocities are high enough, it'll flow as a stream on the outsides of the pipe, with the gas mainly going through the middle of it. Any liquid that's injected in the system is just going to mix with that liquid. So if you're injecting scavenger and you're spraying it in, it's just going to get stuck in that liquid. It's not contacting the gas. It can't do its job. If you have a fog of condensate where you've condensed into where it's actually condensing out of the gas stream and it's not just on the walls of the pipe, then you're injecting, a fog of scavenger in there. It's just going to mix with those droplets too. And if the chemical can't touch the gas, then for H2S scavenger, it can't remove the H2S because it can't touch it. Scale inhibitors need to be, they need to get on the pipes. Corrosion inhibitors, they, to do their job, they can't be washed away with condensate. So, pre-removing that before we try to do what the chemical injection was trying to do was important to get the best efficiency out of that scavenger. I mean, the stuff's not cheap and it's only gotten more expensive. And so if you have to double your injection rate to be able to treat in the time that you need to, that's a huge OpEx that you're adding on to your location to be able to do that. Whereas if you could just separate ahead of it, get that condensate out of there, and then do the ejection, can save you quite a bit of money. And that's what we found on these sites, is just get that condensate out of there, and then we saw an improvement in the chemical injection systems.
Yeah, absolutely. Well, and on the amine plants, let's talk about temperature effects on amine plants. Or if people aren't familiar about an amine plant, can you kind of go into what an amine plant, what's the purpose of it, Charlize?
Okay, so for your amine plants, you're going to be addressing sour gas here, CO2 removal, H2S removal. And so in regards to cooling here, your unit, similar to, your TEG contact tower size, it's going to require a bigger contact tower in order to get that better absorption and contact. And so, you're going to want to cool your gas going into there. I guess, you have your sort of positive and your negative effects. You can go in too low into your amine plants, but, right now we're just talking about ideal temperatures here. So like, in regards to consumables, your lower sour gas temperature will allow your lean amine, your temperature approach, which, kind of ideal there. Maybe your amine temperature is going to be about 10 degrees higher than your gas. And so then it's going to just maintain a better temperature for both your amine and your gas. And this helps, with your concentration levels in your amine. Your temperature is just right and stays and does what it needs to do in the right place. And again, here, similar to your TG with your wear and tear, viscosity comes into play again. If you're too hot, then you're going to be overworking those pumps. And again, with your instrumentation, same thing. If you're too hot, your instrumentation is going to have those issues with that.
Sorry to cut you off when you were just talking about it, but like MDEA, MEA, when type of amine that you're utilizing in it, does temperature actually affect like how
The absorption of it?
the absorption of the CO2 or H2S, does it actually affect it?
So I don't know if there's a difference between DEA and MDEA, which are the two that we normally use. But there is an upper limit to what they can absorb. Like they'll start, your absorption capacity starts to decrease as your temperature increases above, I want to say 140. To the point where I think if you're at like 150, 160, you won't absorb anymore. So if your gas can be too hot coming into an amine plant to where it won't actually do anything. And amine, unlike glycol where you're boiling it out at like 375, amine you're boiling it out at like 210, 225, something like that, depending on your reboiler pressure. So you're not much of a temperature difference there as far as when your absorption versus your removal out of it. But yeah, you can definitely be too hot coming in the system where you're just not effectively. And we had issues with that on some quotes we did for the Middle East after compressors, trying to do some fuel gas for them, removing like high amounts of H2S, and we couldn't get without a refrigerated cooler, there was no way to get the gas cool enough for the amine plant to even do what it was supposed to.
Well, then, do you have to turn up the temperatures? Like I know on a dehy you have to, just to try to maintain the amount of water content that's coming through with the temperature increases. Do you have to do that with an amine plant just to maintain? I guess you're working the pumps harder, so you would have to turn it up more.
Well, if you have it real hot coming in, it means you hit your flash separator first, and so you're going to flash off some of the gas. If that gas is 140 degrees versus, which you're going to have some heater reaction with the amine too, so the amine is just going to get hotter. It's going to be hotter coming back to the plant, to the regen than it did going into the tower. All that flash gas, if it's hotter, it's going to pull more water out because it can hold more water. It's low pressure. It's going to suck more water out of your amine. If you can't condense back down very well, then you're going to run into other issues where you're losing water out of your plant too. Hotter gas, if it's hotter but dry, it's really going to suck water out of the amine plant, which means you're going to have to add a lot more DI water back into your system, which can be problematic depending on the availability of that and stocks and cost of that if you have to have it get delivered. But as far as like operations, you still operate your reboiler at the same temperatures and everything. You have gas or you have liquid heat exchangers, and those are going to have a hard time cooling that back down again. If it's 160 coming into the exchanger, you're not going to get below that on your lean amine going back to the pumps, and so your lean amine cooler has to work harder. Your pumps get hit hotter, which means they wear them out faster. All those seals and everything, I think the chem rays aren't really supposed to be run over 140, and when you do run them over 140, you definitely notice your rebuilds increase a lot.
Well, I know there's a lot of variables. I mean, even sea level of what temperature you're supposed to run the reboiler at. But what is a good, I guess, average temperature you'd like to at least the text to start off with?
I mean, we usually target around like 125. Our reboilers run a little lower on our little plant. But yeah, it depends on your operating pressure, your reboiler.
Okay, so it's at 125. Hey,
Or
Charlize,
225, I'm sorry, 225.
225.
Yeah,
What's
225, 230.
Charlize, what temperature do you bake 2 pies at?
Bake 2 pies.
Think engineering.
Is that something to do with 3.14?
6.28 is what somebody put on the chat.
Yeah, it's 360 degrees.
Oh, God. Why did I
I was
think
thinking
of
of the
that?
wrong pie.
How's
Yeah.
What's the scoff? The scoff
That-
level, 1 to 5.
That one was a 5. That one was a 5.
Okay, it's pretty good scoff. Okay. FCS. So I know people have developed fuel gas conditioning systems. It's all about, fallout before it goes into the engines itself. Talk about, we got a lot of these in our lease fleet. Temperature is a huge effect on this. So Shirley's kind of kick this one off on this product line. It doesn't have to be a full FCS. It could be other things they've developed, but kind of go through this.
Okay, so for your FCS, when addressing your unit, cooling, it's always cooling or separation after cooling is always just kind of a good first step. Similarly to your JT, if you have an increased inlet temperature, you're gonna have decreased amount of recovery there. Your wear and tear, same thing. I probably just don't have to say that same part over and over again, but in this case, you're just not going to be meeting spec for your fuel gas. And so cooling is a good first step here. And then you're going to achieve what you were wanting to achieve for your efficient system.
Well, like we were discussing on the first one, which is separation, just the 5-degree difference between the 4 separators, you were seeing massive fallout into it. And then the reason we developed FCS units is because before it goes into the compressor, falls out in the Big Joe, locks everything up, either liquid, turned into hydrate formation, or just complete liquid fallout and staying in liquid. But Chris, can you kind of go through, everything we're doing is manipulating temperatures, right, on the FCS unit?
Yeah, and I mean our FCS unit has a JT unit in there. Our smaller ones have like a dehy vessel and an ambient cooler on there, and the whole idea is to pre-cool it to something reasonable, dry the gas, and then JT it get as cold as we can. With fuel gas, your target, from a safety standpoint, just operation maintenance, running your engine effectively, you can't have liquids in it. It's a gas engine. It runs on gas fuel. You can't have liquids going in there. So as opening up that delta of your hydrocarbon dew point, so that, if the gas is coming in, the coldest it may ever come in at 40 degrees. So if you have a 20-degree hydrocarbon dew point, you're safe by 20 degrees, right? Because the gas will only ever get down to 40 degrees. It'll never get to 20. You'll never make liquid. And that liquid won't ever end up in your engine, potentially blowing up your fuel train. So that's the ideal, that's the first step to making sure that your fuel gas system is doing what it's supposed to. Then it turns into like a BTU issue. Do you need your BTU real low? Does your engine need a certain low enough BTU for knock issues or WOBE issues or just combustion issues? But yeah, making sure that you don't have that liquid fallout, that's the whole thing. And the colder you get, the more liquids you remove, and that bigger that window is that you have. So the cooler the temperature coming in, the colder the system can get, and the more effective, the cleaner burning, less emissions, all those benefits that come with burning lower BTU gas.
Yeah, the FCS has worked out extremely well for us for compressor companies. But we've seen, you don't have to go full on like the picture you see here. We've seen people where they just hook up almost like a back pressure valve and have a small catch fuel pot before it went into their Big Joe. It's just all about just remove as much of the liquids out as possible, affecting that temperature. So natural gas coolers and utilization, we broke this up into 3 non-powered coolers, powered coolers, and refrigerated coolers. We're going to go through these pretty quickly on, because I know a lot of people know about it, but the non-powered coolers, Charlize, can you talk a little bit about this?
Okay, so these next few slides, what they'll address is just kind of like when, when you're going to choose which type of cooler you're going to need and what's going to affect that decision there. Your non-powered coolers are going to be passive cooling, so there aren't any moving parts to it. You don't have any power requirements there. It's ambient. It's just your air. It's your outside temperature. You're not going to have any emissions on these, so there are less restrictions to those. That's a benefit. If you did have any emission restrictions, then these are a good way to go if you can utilize them. If your gas temperature going in isn't too high and your pressure is okay. And so these are going to generally be for lower volumes because you won't be able to get that proper cooling effect that you desire if your volumes are too high going through these. And kind of touch that a little, the environmental and seasonal part, of course, here, South Texas, Louisiana, with your 100-degree temps and, peak summer with 100% humidity, you might not achieve that cooling effect that you're looking for. So, if you have this cooler somewhere up north a little bit, it's going to do a little bit better job doing what it needs to do. One of the benefits for a non-powered cooler is that air is everywhere. And so as long as you have that proper circulation, there aren't those added costs there where you're going to need some, created airflow there. They may require a larger footprint though, because if you say you have those restrictions or no power for your coolers, then you might need to put multiples to try and achieve that temperature that you're looking for.
So non-powered, Chris, anything you want to add to that?
Typically we see a good application size is higher pressure, and then 5 million or less is usually kind of where we see the breakover for these non-powered ones. And I mean, it may even be lower than that depending on the ambient conditions.
We got the pros and cons, and then powered coolers. Chris, you kind of want to take the lead on this one?
Yeah, so powered coolers.
No, go ahead. Sorry.
They come in a lot of different sizes, shapes. Either electric or natural gas driven with an actual engine attached to them. The electric ones can be efficient. Especially if they have a VFD with a temperature controller on them, then the fan runs exactly however much the temperature you want to maintain is. These are get you into the higher volume. So once you get past that 5 million, usually the powered cooler is the way that you're going to need to go for that. They make their own air, so it's less dependent on the ambient conditions that you have, but higher humidity is still going to derate that a little bit compared to areas with lower humidity and different ambient conditions. But you're still only as good as your ambient air. So you're not going to get below ambient conditions with one of these just powered fan coolers. But yeah, depending on how you want to power it, we kind of like the electric ones. They give you a little more with the VFD and temperature control. They give you really nice control on your outlet temperature. That way you don't get too cold. They're very power efficient if you can get the electrical power out there for them.
Now you can get. You said that earlier. I've had to talk to a few people about that. So you can get within what, 5 degrees, 10 degrees of ambient if you have a powered or non-powered.
Depends on if you're oversized or not. You can get pretty much to ambient if you're cooler, 20 million cooler only doing 5 million. But yeah, generally the rule of thumb is most of the exchangers are sized for like a 5-degree approach on what your ambient is.
It's we've had a few clients where they're coming in. I think because you're talking about cooling, that they think they can get cooler than that, so they want to go below ambient and almost like a chiller. So I guess that moves on to the refrigerated coolers. Can that get below ambient?
Yes.
That's just an air conditioner. Okay.
Yeah, so that you have an actual refrigeration system on it. So that means that you can get with that refrigeration system, however much tons of refrigeration you have, you can get cool. You can get way below ambient down to 0 degrees if you wanted to and turn it into refrigeration, actual refrigeration unit. But yeah, I mean, this is, if you have real high ambient conditions, like some applications we were looking at in India, this was kind of the way to go for them, just because they have real hot, very humid ambient conditions, and they really needed, for the effectiveness of the JTs they were trying to run, they really needed to get down even lower on their inlet conditions. And I mean, after compression just gonna add a lot of heat to the system, and if the fan coolers on the compressor, you know, can't do much if it's 125 degrees outside with, you know, 100% humidity in some of those areas. So yeah, refrigerated cooler is really the only way to go.
So those are the 3 categories that we have. So it's non-powered, powered, and refrigerated coolers. The next section that we're going to be talking about, we're breaking it down again, is design requirements. So the big things, I guess, for proposals, right, Shirley's? Like what you need, common issues, and then basic troubleshooting that we've seen. So design requirements, Shirley's, you do a lot of our proposals. Actually, you do all of them. So on this, can you kind of go into the design requirements? What do you need for you to do your job?
So you're going to need, 3 major things. Will be your inlet volume and your inlet pressure and temperature. Those things are going to contribute to, let's say if you have the proper power requirements in your volume, in a substantial volume, can we get a powered cooler out there for you? Is your pressure high, too high, maybe too low? That's going to depend on, how your tubes, their tubes in your cooler, how big they're going to be, how small they're going to be. And then of course, inlet temperature, how high is your inlet temperature, and then your output requirements, how low do you need to get your temperature? And then other things to consider in design would be the area that you have. Do you have enough space to fit, this standard ambient cooler or powered cooler? Do you have the space for it? Do you have the power requirements? And then what are your conditions? Here in South Texas, where we might have this non-powered cooler, and it, during peak summer, if it just gets way too hot, it just really is not going to achieve what it needs to achieve. You might need to go the powered direction, or maybe some other sort of troubleshooting to get that desired temperature that you're looking for.
So I know if they're having temperature effects, lease operating expenditures, you got operations going in. So these are the questions that people need to be asking themselves if they're having temperature issues. So I know, do you ever deal with Fahrenheit, Celsius? Have you ever dealt with Kelvin?
I haven't encountered that just yet.
All right, so I got this from my son. Here's a good one for you. Do you know why Jedis, you listen to watch Star Wars, right? Okay. Do you know why Jedis do not deal in Kelvin? Because only Dark Lords deal with absolutes. Boom, boom, boom.
That one's like a 4.
4, okay. Right. We still got a winner. All right. This is a fantastic one. Chris, I know you walk through this with a lot of the clients in their initial, they're saying they have temperature issues, and you kind of help guide them through this. What, walk us through this, and how you guide a lot of the troubleshooting issues that you see.
Yes, these are different areas that you could put a cooler in, or may need a cooler depending on what you're trying to do. The first spot would be right after the well, before your initial separation. So if let's say your well is coming out very hot and you want to cool it down there, that is potentially an expensive cooler because it is low pressure with a higher volume. We see that on a lot of applications where it's just kind of a killer when it comes to cost or standard equipment. It's just when the pressure is too low, just because it makes your cooler a lot bigger, because you got to slow the gas down enough, which means you have to have enough tubes, which you can just really grow the size of the cooler required to fit that application. But putting a cooler there would definitely increase, depending on the hydrocarbon dew point, how much liquids you're going to dump out in that separator and add to that separator. And your compressor may or may not have issues with dealing with the amount of liquids it's going to squeeze out. So you may need to cool it down to help remove the liquids going into that. The second spot would be right after the compressor. This is a place we do see a lot. This is probably the more common place to put an ambient cooler on a location, just because of the heat of compression and the compressor's ability to cool down that with its aftercooler may just not be very effective depending on where it's located. And usually the compressors have like a 20-degree approach on what they're trying to do. So if it's 100 degrees outside, their goal is only to get it down to 120 on that discharge gas. And that's like the standard compressor aftercooler. So it's not going to do all that well. And 120 is pretty hot when you have other processing equipment down the line. So your aiming plan, if you have that cooler number 2, then your aiming plan's kind of covered if you have one. The real benefit, or a big benefit of that, is just reducing, especially if it's rich gas, reducing the amount of hydrocarbons that may end up in that plant. Because foaming issues, increased filter wear and tear, potential upsets in your flash separator. If you have that liquid coming into the plant and it's falling out as liquid, you can really have some upsets. And the aiming plants are, they're the most finicky thing that you're going to have out there, and they're most prone to upsets. So trying to reduce what could potentially happen to them, keeping those liquids out that aren't supposed to be in there is pretty important. Cooler number 3, a lot of times that is included with the aiming plant if it's big enough, but really it's an after cooler after the contact tower to help try to recover some of the water you may have lost just because of the heat of reaction with the aiming plant, trying to recover that, separate it, send it back to the aiming plant so that you don't have to keep adding as much deionized water. But that can be important just because the aiming plant may impart a good amount of heat into the system. And then cooler number 4 would be after a TG unit, because the TG unit may also either just be running hot before you go to a JT and you just want to cool it down. I mean, we've seen them where they're coming into our TG at like 125. The TG is not doing anything to help cool that down. And so it's hitting that sales meter at like 120, 121, just enough over to our pipeline saying, no, you got to cool it down. You can't go into the sales meter that hot. So putting cooler before the TG would be the benefit there. But if you have a JT unit, the whole idea of the JT unit or refrigeration is just to get cold. So cooling it down ambiently is a lot cheaper than cooling it down with pressure drop or with compression or for refrigeration compression. So ambient cooler, it's a lot more cost effective to cool it that way and then go into a JT or refrigeration unit than trying to rely on that unit to get you all the way.
No, absolutely. I know. And then you kind of compounding on top of this, you have common issues that you see and that you kind of advise your clients with. Can you wrap up this one as well?
Yeah, so I mean, we see a lot of issues in the summertime. That's usually when the effects are most pronounced. Dehydrates start getting out of spec, or other problems that are created by heat. So that's a more common time when we see it. But usually in the spring and the fall is when we see a lot of when temperatures start changing a lot. It's where we see a lot of the hydrocarbon issues. And so that can be an area where coolers can help with that as well. But yeah, with the coolers, I mean, you got to have airflow. If it's a non-powered one, you got to have that wind area to be able to actually let that air flow through it. Forced air coolers, you still don't want to block those in either. Also, you kind of want to maybe think about where you put your forced air cooler. If it's a through draft where it blows through the unit instead of like a suction or updraft, you may not want to point that at some place where the guys are working, where they're constantly doing it. You don't want that 120-degree breeze blowing over your operators as they're trying to work on equipment. So considerations of where you're placing these units can be important. Making sure you separate after your cooler if it's rich gas. You can make a lot of liquids, and just because you're cooling it down, that liquid may end up, in a pipeline or in your processing equipment. And then the thin tubes, they're very thin, small diameter tubes. So sand issues, you get frac sand upsets that can scratch through those tubes. Checking them, make sure you need to check those for leaks and make sure that they're not leaking through. Eventually it can erode out and you can have a pretty big problem. But yeah, you don't really want liquids going through most of the coolers. And most of them aren't designed for liquids. So that's something you really want to separate before and then look at separating after for these ambient coolers. But you get rid of the liquid beforehand, the cooler's just going to work better anyway.
Well, we got the case studies kind of going through this. Charlize, can you go off the first case study, the top one? Or I think
Okay,
pretty well these are issues we've seen, and I actually got some funny ones I want to talk to you about after.
Okay, kind of similar to what was said on the dehy page. You know, coming in really hot, too hot into your vessels is going to require a lot more EnviroDry, which is the desiccant. And you know, you put an ambient cooler before your PDS system and drop it to a more efficient temperature going in. And so for this particular example, it cut the EnviroDry to 1/5, and that, you know, that's going to cut down a lot of costs for you, and especially if it's your monthly maintenance or however often your maintenance is, that's going to cut a lot out for you.
The second one, Chris?
Yeah, the second one was the client came in and added compression, which boosted their volume as well, which the TEG should have been able to handle, but with the heat that was coming off the compressor, it just wasn't able to maintain spec. But the cooler, adding that cooler in there, and then the separator after the cooler, really helped to reduce that temperature load and made that TEG able to do what it was designed for. Or else, yeah, they would have been looking at having to bring in a larger one.
And then on the last one, Charlize, can you go through that one?
Okay. Yeah, you know, just again with your cooler before your FCS unit, and that way you can, if you have an ideal temperature, say 100 going in, then you can achieve those cold separation temperatures after your drops. And you know, that's the difference between if you require your cold separation to be, you know, -10 or going into your negatives and even staying positive to get all that, you know, liquid recovery, your BTU reduction that you're looking for after your system.
So I want to create like a funny use home videos of things that you've seen out in the field, but I don't want to be just, you know, hurtful or anything to the operators. But Chris, there was that one client that put a compressor and then it was blowing all of its exhaust straight onto they had a cooler, and it was actually just warming it up. So it was like, that thing was blowing at 160 degrees right onto their cooler, and it was actually warming up the gas.
Yeah.
And then, dang it, what was the other one that was funny? Not funny, but I guess it was funny to me.
Well, we had one operator put a sprinkler on our non-power cooler. They just fixed it so it just poured water out and you saw the dribbling water over it, which is fine if you had water. And one of the other operators, they put I've always seen them put cooling loops in before, you know, dig up, you know, 5 feet down and put in a couple 100 feet of pipe, which can be an effective, cheap way to cool down. But this operator had a ditch on 2 sides of their pad, and they ran the pipe in the bottom of the ditch. And then they had a little water well, and they would just fill it with the water well. The operator wasn't happy because he had to bring his generator out to power the water well. But it worked as long as the pipe was submerged. But when it, you know, boiled all the water off or, you know, evaporated it away, then it didn't really cool too effectively. But
well,
it was cheaper than bringing the
also we did find out, that's why we started putting roofs on all of our stuff. We found out radiant energy plays a huge part of it. We went out to location, there was a cooler that was sideways, looking directly at the sun, and we were finding out that radiant energy was actually heating it up. It was going in at a cooler temperature than it was coming out of that cooler. And that's what actually, Chris, you and I were talking about, we're like, man, maybe roofs are important. And we started, that was like 10 years ago, 12 years ago, and we started putting roofs on all of our 8 ambient coolers that we were shipping out.
Yeah, I mean, we had one operator see it and be like, man, that's a good idea. You have a roof on yours. So they put a tarp over theirs, but it didn't have the frame. So it ended up just being a tarp over the cooler, and it just all it was insulated. Just
so no
airflow. Yeah.
Well, you know, that's one thing to consider when you're, you know, and in your design criteria is that, like, even let's say if you were to put your cooler under some trees where there was a little bit of shade, but then it might block out your airflow. So, you know, it's just a lot of things to consider and make sure that you where it's going and how your arrangement and where is it going in the plant. And like you said, with that compressor air, it's just like blowing on it. And
each area is different. Like Eagleford, we have one of our business developers, and she was saying it's 160 degrees down where she's at in Crystal City area. But, you know, there's nothing out there. So you get a lot of wind blowing, but it's still very, very hot out there. And then we got the clients in East Texas that have a cooler. I guess it's a little bit cooler, but there's so many pine trees that they put a cooler out there, but there is no air movement. So you can't even dissipate any of the heat off the cooler. So it's just interesting. I guess you got to work with what you got to the best of your ability. Well, in wrapping this up, if you have any questions, please feel free to reach out to us. Specifically, if you have one that you really just want to talk to Chris or Charlize about so they can get the answers back to you. I know I said a lot of jokes and puns today, Charlize, but I thought they were pretty cool.
I'm surprised you just didn't have something out there about hot gas.
Oh, I probably should have done that. See, that would have been fun. I need you to write the...
Well, full of hot air, aren't we?
Yeah. Well, I'm not a politician. I'm not going to say a lot of hot air. So, but I appreciate everyone coming today, talking about it. Now, the whole purpose of this is we want all of our clients and all the people to be as successful as possible. I hope everyone becomes millionaires. The only way we could do that is to make operations more efficient. So if you have any way of wanting this information delivered to you a little bit better, or tailored to improve upcoming webinars or, you know, roundtables that you have, please feel free to ship us your feedback. So that way we'll ship you a hat and a shirt, but that's the only way that we're going to get better for you. Do check out our resources. We got a lot of videos. This is actually our 17th episode for webinars alone, but we have a lot of other videos that we've shot, a lot of blogs, information that could answer a lot of the questions. But if you want to get down and dirty and get a very specific question, please feel free to contact us, and then we'll make sure that we have the questions answered for you. But thank you again for everyone joining us on the webinar today. And then we hope to see y'all again here in 2 months. All right, take care.